Don't have the test graded. In fact, I haven't started yours yet because my Algebra 2 students finished up their test on Tuesday. I finally got those finished up last night, so we have conferences tonight, so I can't get going on your tests until tomorrow. Hopefully, I'll be able to take care of them. If latest, probably Saturday. I'll get your scores in there. And then I'll also be putting a folder on Schoology if anybody is interested in retakes. But hopefully, they're all A's and they're all perfect, and we don't even need to talk about any of that. So, like I said, extra 2 sheets of graph paper on there are for the homework, not for the notes. And the one page that was at the end of your section 4.3 that had the unit circle on there, that's for you to kind of go through. I'm going to skip ahead and just start talking about how we graph sinusoids. So that's what 4.4 is about, us getting used to the graphs of sine and cosine. And we've shown you some graphs before where you realize tangent is a different animal. It really is. So sine and cosine fit together in this group of graphs called sinusoids. We want to be able to review those basics of the unit circle because that's where the graphs of sine and cosine come from. And we want to understand those graphs. How do we graph them? We're going to be doing that in great detail by the end of these 4 days. Graph sinusoids and their transformations looks a little scary when you see our 2 generic forms here for sine and cosine. But the good news is we already know what A does. That's always been where we look for the vertical stretches or vertical compressions. That's not changing. That's the same thing. H and K doing the same stuff they've always done. Don't forget that X is naughty, and whatever we see with X, we have to think the opposite of what it is. So if it says X minus 2, it really means it's going 2 to the right. This is the one piece that's going to be a little different for us, and that's this gigantic B that we see in front of both of these. And that has to do with a horizontal stretch or compression. And so we have to fit all of this together, but we're going to do baby steps, and we'll get there. Amplitude. We're talking about sound waves. That's what sinusoids are. They're sound waves. That's how we describe sound. And the amplitude is really how high and how low does the graph go. I mean, that's going to be amplitude, the height of our graph. The period, I've talked about this before, that's how much you need to copy and paste so that you could make the graph go forever in each direction. And notice this has 2 pi over the absolute value of B, because B is responsible for that horizontal stretching or compressing, and when that happens, that's going to change what we have for our period. And then a phase shift of H, a vertical shift of K, totally used to that. And modeling periodic behaviors with sinusoids, way in the future. We've got at least 3 days here before we can start working in the word problem sector. So this is the page that I was talking to you about that was at the end of 4.3, and you're certainly welcome to go back. It's really good practice, to go back into the unit circle and fill in that you've got your 1, 0, square root of 3 over 2, 1/2, square root of 2 over 2, square root of 2 over 2, 1/2, square root of 3 over 2. And like I said, just, good review to go around and think about the symmetry that happens there. But where we're going to get all of the things that we're doing graphically comes from the fact that the x-coordinate is the cosine of theta, and the y-coordinate is the sine of theta. So if we're graphing these, we need to know what the angle is in radians, and then we need to know what those coordinates will be. So for the position that we have right here at 0 radians, we see that cosine starts at 1, while sine starts at 0. And you can use those coordinates to get a graph. And usually we're not trying to graph things like the square root of 3 over 2. That's just something we leave out. We try to graph the nice points. And once we have those nice points, then the rest of this just falls into place and happens naturally. But down here, things we definitely talk about when we start looking at the graph, the domain. The domain for theta is negative infinity to infinity. Again, we're going to talk about theta in terms of radians. We want these graphs to be exact, and that means we're going to use radians. And the range for y equals of cosine of theta and sine of theta is from -1 to 1. because if we go around the unit circle, that's as big as they get and as small as they get. And then going from 0 to 2 pi completes one full circle when we're not talking about having any horizontal stretches or compressions. The graph of y equals the cosine of theta can be found by graphing all the points theta and x, so the x coordinates of everything on the unit circle. And then the graph of y equals the sine of theta can be found by plotting all of the points theta y, because all of those y coordinates are the sine of theta on the unit circle. But again, we have a different process for graphing it than we do for going around the unit circle, because we're going all the way back to the 30, 60, 90 and the 45, 45, 90 triangles when we talk about our unit circle. We want to leave the triangles in the dust. We really do. And we want to say, okay, what can we learn that's specific to the sine and cosine graphs that will help me do this whole process a little bit faster? So it does go back to the unit circle, but we get a little detached from it for a while we talk about the basics of the sine and cosine graphs. For the basic sine and cosine functions, the period is one full circle, which is 2 pi. So this is before we do any a, b, h, and k, that we have one full circle, one full turn around it, I guess I should say, in order to get all of the numbers that we want to get a really good graph of sine and cosine. So, I guess I could put it in this little slot right here. There's our 2 pi. Now, to graph it. Again, we don't want to have to graph things like the square root of 2 over 2, the square root of 3 over 2. It'd be nice to just use things that show up decent from what we have here. So I start thinking, where are the nice x values? You know, where does it land on something really good? Well, here we've got a 1, a 0, a -1, and a 0. Those are nice numbers. I'd like to graph those. So while we're using the unit circle, we're going to take the things that work out nice. We're not necessarily going to take the square root of 2 over 2. So to graph it, the first thing we do is divide it into 4 equal increments. So in this case, if our period is 2 pi, we're going to divide it by 4 and get pi over 2. I do want to let you know that most of this works with fractions. And I know it says divide by 4, but if you're going to work with fractions, it's most of the time easier to think of it as multiplying by 1/4 instead. If you're working with fractions, it helps your thinking process a little bit better. And then you mark these increments on the x-axis. So it's 2 pi over 4 gives us pi over 2. So what we want to do is come over here, and that's theta, so that's our x coordinate. We want to mark 1 pi over 2, 2 pi over 2, because we're supposed to use pi over 2 for an increment. That really is telling us horizontally that's the piece that we want to use for the distance between those points. So 2 pi over 2 would be 1 pi, 3 pi over 2, and 4 pi over 2, which is 2 pi. Now we know that it's going to go as high as +1 and as low as -1 by looking at those x and y coordinates as we go around. So that's going to be what I use on my y, is a +1 and a -1. Now we switch gears because we actually want to do the graph. So, like it says, we're going to determine the starting points. Sine always starts at 0. Remember this first point out here is cosine theta. That's that blue again. I should just tape over the blue. Blue, you let me down. So that point that we have over there at 0 is telling us that cosine is starting at 1, but sine starts at 0. Now with sine, starts at 0. And from there, sine is axis high, so it'll go up to positive 1. Axis low, down to negative 1, and back to the axis. So there's that oscillating. And we want to make sure that this does not look like a zigzag. We don't want this to look like Charlie Brown's shirt. We want this to look like a nice smooth curve as we graph it between negative 1 and 1. And like I said, the rest of this is just going to come naturally, you know. If we were to look at pi over 6, we would see that sine should be at 1/2. But we're not going to put all of those itty-bitty little details on our graph. Our graph is about the overall picture of the sine graph. So again, Charlie Brown's shirt has the nice zigzags on it. We don't want that. Try and make it look like a nice smooth curve. It takes a little bit of practice. So f of x equals the sine of x. And we've got determine the starting points, plot the 5 key points. Well, that's what we just did. 0, pi over 2, pi, 3 pi over 2, and 2 pi. Got them all on there. Connect the points with a smooth curve. Yep, done. So now we need to talk about all of those analyze pieces that we've always done in the past. And for the domain, remember we have coterminal angles, and this thing can go on forever. Theta can go on forever in terms of pi, but not the range. The range is going to be between negative 1 and 1. And that goes all the way back to a triangle, realizing that opposite and adjacent are always going to be shorter than the hypotenuse. So it goes between negative 1 and 1. Continuity. Definitely. We're not lifting up a pencil at any time to draw this. It was nice and smooth. Increasing, decreasing. Well, most of the time we just say none, but this one we can say it's alternating in periodic waves. We can be a little bit fancy with it. Alternating in periodic waves. And alternating got spelled really interesting there. Alternating. There we go. In periodic waves. It does have an absolute max. The highest point that it reaches is 1. It does have an absolute min. The lowest point it reaches is negative 1. Symmetry. So this one, let's think about it for a second. Remember, our choices are even, odd, neither. And even symmetry means you could reflect it over the y-axis and get the same thing. Well, that's not going to look like that because it's going to go down here. So this one's not even. And then you think about 180-degree rotation. Oh, yep, that's going to match. This one's odd. Bounded. Yes, 1 and negative 1 are top and bottom. So I'm going to write bounded. Horizontal asymptotes? No, there's nothing stopping us horizontally. Vertical asymptotes? Can keep going forever. So these are none. And then that end behavior piece, which not everybody was too fond of with this graph when we were talking about the 12 basic functions, because it doesn't exist. You know, the end behavior, it's going down, it's going up, it's still oscillating there. So what we say is does not exist. But that's not enough to describe somebody what's going on with the end behavior of this graph. So we'll say it oscillates between negative 1 and 1. And that gives them a better picture of what's happening with the y values as this graph continues on. So these are the steps we're going to use whenever we're graphing a sinusoid. We're going to divide whatever the period is into 4 equal increments. We're going to determine those starting points with sine starting at 0 and cosine starting at 1, unless we have a horizontal shift. That may change. We're going to plot 5 key points, nice points, like it says, the x-intercepts, the maxes and mins, all that good stuff, and then connect them up with a smooth curve. Sine graph, everybody. Meet cosine. Very, very similar, obviously, to what we just had when we graphed the sine graph. So this one says divide the period into 4 equal increments. Well, 2 pi divided by 4 is still going to be pi over 2. So 1 pi over 2, 2 pi over 2, which is pi, 3 pi over 2, 4 pi over 2, which is 2 pi. Cosine is still going to oscillate between 1 and negative 1. But cosine doesn't start at 0. Cosine starts at 1. Remember that point out there at 0 radians is 1, 0. So it starts up here. So the way cosine works is cosine is high axis, low axis, high. And again, connect it up into a smooth curve and watch the arrows at the end. Don't make them look like they're going, way up forever and down forever. That's not happening. We have to keep that nice smooth curve going. So the difference between the sine and cosine curve is always that starting place of sine starting at 0 and cosine starting at 1. But it's not difficult to figure that out when you just quickly think about, hey, here's my xy axis. This would be the first point on the unit circle that I would use. Cosine and sine. Cosine is 1 and sine is 0. So like I said, we get used to these steps. We're going to see a lot of repetition over here for domain range and all of that wonderful stuff. Domain from negative infinity to infinity. Range, negative 1 to 1, including the negative 1 and 1, so that's the square brackets. Still continuous. Didn't have to lift my pencil or marker up at any point while I was drawing that graph. Increasing, decreasing, again, we know it is. We're going to have to put alternating and periodic waves. Absolute max, still 1. Min, still negative 1. Symmetry is different though. This one, if we take what's on the right side of the y-axis and we reflect it over, it's going to match. This is even. It's bounded. No horizontal asymptotes, no vertical asymptotes. And again, while the end behavior does not exist, we give a little more detail and say it oscillates between negative 1 and 1. So far, I'm hoping you're not too fearful of the sine and cosine. I mean, we just had to learn the basics, These are the basics of how you graph that. But of course, we have to start making changes to that because numbers show up in sinusoids, to make things happen. One of the really unique things that this is used for is separating aluminum from the garbage for recycling. The only way to get aluminum to separate from other metals, because it's not magnetic, is to ping it with sound waves. So the sound waves hit it, and the cans actually fly up in the air, and they catch them in a net, and that's how they recycle them. So like I said, some very, very cool things can happen when you're talking about trigonometry. Alrighty, they've got a big blue circle on A. Okay, well, it's not the A we know before because that was a lowercase a. It's a capital A because it has a special name. Sinusoids, that capital A is known as amplitude. That's our height of our graph. So they're saying we're going to change that from 1 to -1. Now we're going to vertically stretch that, or we're going to vertically compress that. And A is responsible for that piece. So A is the amplitude, vertical stretch, compression, and I know that, we put this up here, a reflection over the x-axis. That's not what A does. A is just that height. So when we see this, we're going to need to think of the absolute value of A. If there's a negative out in front, we know there's been a reflection over the x-axis. It's just that A is responsible for just the height of the graph. So down here, example 1. Find the amplitude of each function and use the language of transformations to describe how the parent function is transformed to the given graph. My advice for this one, if you do happen to have some other colors with you today besides just a pencil, I would grab that. If you don't, you're going to want to think about graphing one of these maybe dashed, another one dotted, stuff like that, so that you can tell the difference between these graphs. It's really going to make it pop out at you. Even if you have a highlighter, you could graph it and then you could highlight over the top. Find the amplitude of each function. I'm going to start there. For this first one, it's a 1. There's nothing in front of it. It's a 1. For the second one, and I'm color coding, so I'm going to make everything with this first one red. For the second one, I'm going to go with black. So the amplitude of that graph is a 3. And then, even though I hesitate, I'm going to go with the blue. So my blue one, notice that's a 2, not a -2. Amplitude doesn't get the negative. But we should take a look at this and say, oh, that means I'm going to have a reflection over the x-axis, which is the next thing they have us do anyway. So, back to the first one. Use the language of transformations to describe how the parent function is transformed to the given graph, and graph all 3 functions on the grid provided. Well, this isn't a transformation, this is the parent. Y sub 1 equals sine of x. That's the parent. Now this is really nice. 2 pi divided by, well, in this case, since there isn't any number in front of the x, our b is a 1. So we get 2 pi for the period. And we said either multiply it by a 4th or think about dividing it by 4 to get your increments. Well, they're already labeled this time. That's really nice. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. Those are taken care of. I'm thinking in advance about the fact that I have to graph the parent function, then I have to have an amplitude of 3, and then I have to have an amplitude of 2 with a reflection, because I need to label my y's. And if I'm going to get all of that on there, I probably better just go by ones. So let's start at the beginning with the sine graph, which starts at 0. Axis high, axis low, axis. And then you want to continue that pattern off to the left-hand side, because we don't just want always the positive look at it. We want to see what it would be as we go into the negative x values. And then, like I said, if you don't have colors, maybe make this one dashed or dotted or something like that. But make that nice smooth curve as best you can. And label that y sub 1 equals the sine of x. Now there's a nice little mnemonic to help you remember what we're talking about as we go axis high, axis low, axis with sine. And you have to think of this as speaking Hawaiian. It's called Sahala. Sine is axis high, axis low, axis. Sahala. And that usually helps people out a lot. Although it's not too hard to think of the fact that over there at 0, you've got the point, 1, 0, and it starts at 0. But this helps students a lot, Sahala. So we've got that one done. Now, I go to the second one. Use the language of transformations to describe that function. Well, that 3 in front, that's a vertical stretch, factor of 3. Remember, when that number is bigger than 1, it's a stretch. So vertical stretch, factor of 3. Wow, that complicates things. No, it doesn't. Because all it means is wherever our y's are, we're going to multiply them by 3. And remember, we have some really nice y's on here. This is at 1. 1 times 3 is 3. This is at negative 1. Negative 1 times 3 is negative 3. The others are 0. 0 times 3 is still 0. They're not going anywhere. So we just need to change our low and high points. But the zeros are staying exactly where they were. And again, connect those up in a nice smooth curve. If you don't have extra colors, maybe do this one solid. Again, try not to look like Charlie Brown's shirt when you're done. And label it. So now we can really visually see that vertical stretch, factor of 3. If this red graph were made out of rubber bands and you grabbed the top and the bottom and you stretched it 3 times its size, it makes sense. That's what it would look like. Over there with C. Talking about transformations, the first thing we see from left to right is that negative. So we have to say reflect over the x-axis. Then we see the 2. And the 2 is a vertical stretch, factor of 2. Okay, so if we're going to have to reflect it over the x-axis, that means our highs become lows and our lows become highs. And because we have a vertical stretch factor of 2, it's going to be between negative 2 and 2. So this will now be down here. And this low point will now be up here. Again, the zeros are going to stay where they are. 0 times anything is going to be 0. But the highs become the lows, and the lows become the highs. And then we try to connect them all up with a nice smooth curve. And label. So you'll notice you can't use Sahala when there's a reflection. You have to think about the fact that it's been reflected over. And so the highs become the lows, and the lows become the highs. But with that one as well, you can definitely see the reflection, and you can definitely see the vertical stretch, factor of 2 for the amplitude. So again, amplitude A is never going to be negative. It's about the height of the graph. You know, how tall is it? Well, 0 to 3, so 3 units up and 3 units down, and that's our amplitude. Well, that wasn't too bad. That was all sine graphs. So let's take a look at cosine. Same thing. Let's try to color coordinate here. Find the amplitude of each function, and like it says for y sub 2 and y sub 3, use the language of transformations to describe how the parent function is transformed to the given graph, and then graph all 3 functions on the grid provided. Well, this is the parent. So its amplitude is still 1. It's like there's a little imaginary 1 right in front of here. But there's no transformations. Again, they already put those intervals on for us. If they didn't, we'd have to go through the 2 pi over b business and see that since b isn't there, it's a 1. And then we'd take our 2 pi and divide it by 4 and get increments of pi over 2. So I know this parent function, high is 1, low is -1, but I want to look at the other two to see what I should do to label my y's. And I see that for this one, we only have to go as high or as low as 2. So maybe we could spread this one out a little bit. Maybe go every 2 blocks. That'll make it a little bit easier to see our 1/2 for y sub 2 anyway. All right, so back to color coordinating, and I see cosine, and I think, okay, cosine. Cosine starts at 1. 0, 1. And cosine is kahala. Again, think about speaking it with Hawaiian. Kahala. So cosine is high axis, low axis, high. Kahala. Follow that same pattern going backwards into your negative x's. And nice smooth curve. And label. Change colors if you got them. Absolute value of A on this one going to be 1/2. So that's definitely a vertical compression factor of 1/2. So we did a little description there. So now it doesn't go all the way up to 1. It only goes to 1/2. And it doesn't go all the way down to -1. It only goes to -1/2. So starting high means it's going to start at 1/2 instead of 1. But 0 times anything is still 0. So any of those that landed on our x-axis, they're staying exactly where they were. And nice smooth curve, that one. And we'll label that one. Y sub 2 equals 1/2 cosine of x. And we'll change colors. And we'll go after C. What's the amplitude for C? Yep, just the 2. What does the negative tell us we're going to have to do as far as transformations? Reflect over the x-axis again. So what's that 2 responsible for, transformation-wise? Vertical stretch factor of 2. So the biggest catch with this one is that reflection. What's the easy way to make sure that's taken care of over there? Yep, highs become lows, lows become highs. And we have to go up and down 2. So here's a high, has to go down to -2, as I'm saying it backwards. Zero is going to stay put. And then follow that same pattern on the other side. Highs become lows and lows become highs. And nice smooth curve as best you can. With your arrows at the end. Obviously reflecting this continues on forever. And make sure they don't look like they're going down forever and up forever, because we know it oscillates between, in this case, -2 and 2. Again, I think it's obvious when you have it all graphed with the different colors that you've got the vertical stretches and the compressions, and you can see the reflections as you go through there as well. So, sine is Sahala, cosine is Kahala. To help us remember, sine is axis high, axis low. Cosine is high axis, low axis, high. Now we have to talk about B and what the role of B is going to be in all of this. So the period or the length of one cycle can change to be longer or shorter than 2 pi. That's your horizontal stretches and compressions that are going to take place there. And this is where, remember, this is all attached to X. See how B is always with the X? So what we see is the opposite of what's really happening. If this B value is a 2, that is a horizontal compression factor of 1/2. Remember, these are about multiplying and dividing. So the opposite of multiplying by 2, dividing by 2, which would be a 1/2. And if the absolute value of B is greater than 1, yeah, that's where we see the compressions, because we have to think opposites. If the absolute value of B is less than 1, well, then your period is going to be longer than 2 pi. So how do we figure it out? Well, the absolute value of B is going to be the number of cycles in 2 pi. That's definitely going to be shortened or lengthened when we have a horizontal stretch or compression. So to find it, what we're going to have to do is use 2 pi divided by the absolute value of B. And you saw me write that down before. Because normally the graph has a period of 2 pi. But if we have a different B value, that's going to change. Now, why that's an important piece is because that changes our increments. That changes where we have our zeros and where we have our highs and where we have our lows. So to graph the sinusoid using a new period of 2 pi over B, we have to figure out what that is, and we again have to divide that new period into 4 equal parts, because we want to know where everything is going to be at. Then we can use Sahala or Kahala, depending on which sinusoid we're going to graph. So example 3 says determine the period for each equation and then graph 2 full periods. And that's usually what we do, even on a test. Normally we'd say, fill the entire grid as best you can with everything. But on a test we'll usually say graph 2 full periods. So let's take a peek. So this is definitely a sine graph. And I see that there's a 2 in front of the X. So that absolute value of B is going to be 2. Now, why do we have to do this absolute value thing again? Because if B is negative, well, then we have to talk about reflections over the y-axis, because the negative would be with the x, and it's always the opposite. But we're not going to do those today. Let's just do these. So the absolute value of b is 2. I need my new period. I better put a capital P there, so when people look at their notes later, they'll go, oh, that's what we were doing. And we divide it by that absolute value of b, which would be a 2. And we get 1 pi. Now the graph is still going to start at 0 for sine. But our increments have now changed, because this is no longer 2 pi. So we're going to take pi and, like I said, either divide it by 4 or think of it as multiplying by 1/4. And we'll get that 0 is the first spot. We're going to have a point. But to find the other ones, our spacing has to be pi over 4 units for each one. So we're going to add a pi over 4, which of course, for the first one, would put us right at pi over 4. So we've got to graph 0. We have to graph pi over 4. Well, that's not enough. We need more. So we'll add another pi over 4 and get 2 pi over 4, which is pi over 2. So that'll be another increment that we need to graph. And we'll graph another pi over 4, keeping in mind that that was 2 pi over 4 before we reduced it. And that'll give us 3 pi over 4. And one more time, so that we'll get 4 pi over 4, which is 1 pi. Now, pretty obviously, you could have done that in your head, and so could I. But when these get more complicated, we want this written out, because this will help us know, all right, for one period of this, I'm going to have to make sure I mark 0, pi over 4, pi over 2, 3 pi over 4, and pi. So that's what we need to do over here, although I don't know where my lines went on this one. Let me see if I can make those a little darker without this taking forever. No, that's as good as it's going to get. That's not good. Alrighty, so I need those marked. I think I'm going to try and go every 2 blocks for these. So I'm using 0, then I'm using pi over 4, pi over 2, three pi over 4, and pi. And obviously, you know, we could keep going with this one. We'd have 5 pi over 4, and then 6 pi over 4, which would reduce to 3 pi over 2, because we could fill the grid. And then we need that going in the other direction as well, because of our nice symmetry. And then we need to figure out, what about that amplitude anyway? Well, there isn't a number in front of it, so our amplitude this time is going to be a 1. So I just need to go up 1 and down 1. I think I'll just make 2 of these. So each one is like a 1/2. Just to spread it out a little bit. All right, I've got all my labels on there. Time to Sahala. So Sahala, sine is axis, high, axis, low, axis, high, axis. And then I run out of space over there. And then we go backwards, following the pattern. And we make ourselves a nice smooth curve. Oh, missed my 0. Trying to make sure it's not looking like Charlie Brown's shirt. Come on, move back. looking like so. So there's our first change horizontally. Now, if you're worried, hey, Cedar Home, that looks a lot like the last ones we just did. All we really did was change the intervals. Yes, but that was the important part. Remember, what this tool was doing here was a horizontal compression factor of 1/2. And now we can see, oh yeah, look at that. One period of this would be from 0 to pi. And we've got it. And that's all we're going to be able to get through today. I have bad news. That means you're not going to be able to do all the homework. I know, I'll make it up to you on another day. You'll be able to do some of it, so you should take a peek. There we go. At 4-4 day 1, 2 through 28 the even, 29 to 34. You'll get to a point where they start talking about frequency, and you'll go, Cedar Home hasn't talked about that yet, so don't do frequency, Do the other stuff that you know how to do, but leave that frequency. I cannot guarantee that I'm going to have the new video up in time for class tomorrow morning. So if I were you, I would sleep in because I have conferences tonight and I have to make this video, and I'm not sure I'm going to be able to do that before we have to be back at 4 o'clock, 4 to 7 for conferences. So maybe expect that it'd be up by like 10 at the latest because I have to do my PLC meeting in the morning before I can make the video. Otherwise, you can use last year's video. I mean, if you're like, I've got to schedule Cedar Home and I've got to keep that schedule just as it is, then yeah, you could use last year's video. But could sleep in a little bit on a Friday. It wouldn't hurt too bad. So, good start. You're not like feeling overwhelmed, right? Sine and cosine, pretty basic now. All right, when we first look at it, sometimes it's, I've never seen this before. What on earth are they doing? But after we go through a few,